Hello, everyone. Thanks for joining us today. Just so you're aware, the link to the Slido is underneath the video on the YouTube channel. So just go on there and post your questions in there as Peter's going through the presentation. So just going to introduce Dr. Peter Irvine. He's a climate scientist and lecturer from UCL in climate change and solar geoengineering. He's been publishing on this for over a decade now and has more of a focus on stratospheric aerosol injection, is my understanding. And he also looks at how we would actually do this, both technically and how to govern the process, whilst considering the broader implications of using this technology. He uses climate models to look at the harms and the benefits of solar geoengineering in areas such as the response to the water cycles on land and sea level rise and ecosystem impacts. And he also works with ethicists, economists, and lawyers to look at how the harms and benefits can be addressed through compensation. And he uses and develops analysis. He develops analysis and visualization approaches that help contextualize the response that solar geoengineering has in relation to climate change. And finally, he's also got a podcast called Challenging Climate, which he does with Jesse Reynolds, who's an expert in international environmental policy, which is really good. So if you get a chance to see that or listen to that, then I highly recommend it. That's in the show notes too. He's I'll leave it there for now and just welcome Peter, and I'll just hand over to you.
All right, thank you, Ian. So yes, I'm going to be talking about this question here. Could solar geoengineering, in particular stratospheric aerosol injection, have a role in future climate policy? So here's an outline. I'm going to talk about Plan A, just to give some context. That is, cut emissions as quickly as we can, use negative emission technologies to draw CO2 out of the air in the long run, talk about how well that's going and what the prospects are. Then I'm going to talk about adaptation briefly and the fact that there will be limits to adaptation and therefore considerable suffering, even if emissions cuts are very rapid. I'm going to explain that while stratospheric aerosol injection is feasible and could offset a degree Celsius or more of warming at a cost of tens of billions of dollars, it's feasible and relatively cheap. Despite that, it is not a substitute for emissions cuts. This is not a plan B for climate. But could it be part of Plan A plus? That is, if we focused on Plan A, did as well as we could on that, and then used SAI, stratospheric aerosol injection, as a complement to those efforts, could we greatly reduce climate risks? And then I'll wrap the talk up. So, Plan A. Yeah, this is, I think, one of the most important figures of the last IPCC report. It shows a very clear message. Every ton of CO2 that we add to the atmosphere adds to global warming. That's what's plotted here. Global mean temperature on the y-axis is plotted against the total amount of CO2 that we've added to the atmosphere. And you can see here in black the observed temperature. You see, initially it's varying very rapidly up and down. And then as we go further to the right, the years are getting further and further apart because we're emitting more and more CO2 each year. So we're moving further along the x-axis every year. But you can see already in the observed record, there is a linear relationship between global mean temperature and the total amount of CO2 we emitted. And then these colored bars indicate projections for future emission scenarios. So in red are very high emissions, and blue are low emission scenarios. And that linear relationship holds. The more CO2 we emit, the warmer the planet gets, and there's a linear relationship to that. That has a few consequences. To limit warming effectively, we need to limit the total amount of CO2 that we add to the atmosphere. Now we can flip that round and go, well, if we want to limit temperature below 1.5 or below 2 Celsius, this relationship can be used to derive carbon budgets. So if we want to limit warming to below 1.5 Celsius, we sort of draw a line from 1.5 across, and go, right, well, that's the middle of these projections. So for a 50-50 chance of staying below 1.5 Celsius, we've only got that much carbon left. So this is a very useful metric. This is basically, in a nutshell, this is the climate problem. We need to get emissions to net zero to halt global warming, and we need to do so quickly if we are to limit warming below 1.5 or 2 Celsius. So how is it looking? Yeah, the Paris Agreement in 2015 set out to achieve either the 2 Celsius or below 2 Celsius or ideally below 1.5 Celsius with goals. And then they made commitments to cut emissions by 2030. So this plot, which is a little bit messy, but I'll walk you through, shows observed emissions in dark blue, up to here, to 2019. And then in orange is the projection of how emissions would continue if we stayed on current policy. So they would rise over the next few years, out to 2030. And in yellow and then light blue are the Paris commitments. If the countries implemented all of the Paris commitments globally, then we would follow this blue line. That is, CO2 emissions would remain the same in 2030 as they are today. Now, this is a long way from what would be needed to achieve 2 Celsius of warming. We would need to see emissions fall by around a quarter by 2030. So we're a long way from being on track for 2 Celsius. And if we want to limit warming to 1.5 Celsius, they would have to fall by 50% by 2030. Simply put, that's not going to happen. We're currently on track for somewhere in the ballpark of 2.5, 3 Celsius, depending on how these near-term commitments, whether they're met, and also the long-term commitments. How do things change by 2050, 2070? So we're on track for substantial warming. We're a long way from meeting these Paris climate goals. Now, that's just a quick picture of where we are on emissions cuts and so on. But I want to also touch on adaptation, on the impact side of things. There's a recent study which I think illustrates a point quite nicely. Wing et al. 2022 projects a 25% increase in flood exposure due to climate change in the US, shown here with this little orange bar. But interestingly, they found that the effects of development, of population growth and new housing, which they estimated would occur a lot in floodplains, would lead to a 4-fold greater increase in flood exposure than the effects of climate change. What this means is that adapting to climate change, it means that there's no such thing as a natural disaster. We have natural hazards, and then we have the human system that's exposed to those. And depending on what we do, if you build houses in floodplains, they're likely to get flooded. If you prevent that kind of development, you can reduce those risks. So to adapt to climate change, we need smarter development, siting things where they'll be less exposed to risk in the future. We need improved building standards. There's not much you can do about a heat wave. It exposes the whole country at once. So you need houses that are better able to cope under high temperatures. We also need, say, new defenses and infrastructure. This is the Maisland Kering, which is like the biggest movable objects in the world are these floodgates that defend Rotterdam. 22-meter tall, heaviest objects that move on the planet. These shut closed when a storm surge comes and protects Rotterdam from floods and from storm surges and projected sea level rise. So we're going to need all of these kind of things in the developed world to help us become more resilient to climate change. But there are limits to adaptation. Now, I'd say poverty is the leading cause of vulnerability. This picture shows you how 2 people or 2 families live in this world. On one side is some of the poorest families in the world in India, so living on the side of a river in a shack made of palm leaves. And on the right is a home in the Netherlands. Now, these same homes exposed to these same hazards, you can imagine the home in the Netherlands is far better able to cope with heat waves, flooding, windstorms, and so on. So economic development effectively is adaptation. The richer these people in India get, the better their homes will be, the more resilient they'll be to climate change. There are also some impacts that are going to be very difficult to protect against. This is the coast of Bangladesh. And Bangladesh is a very low-lying country and very exposed to rising sea levels. Now, we're not going to be able to build a wall around Bangladesh to protect it. It will lose land to sea level rise and storm surges. And in the ecosystem side of things, this is a picture showing a coral reef before and after a bleaching event. There's very little we can do to reduce those impacts of climate change on ecosystems beyond limiting the other stresses that affect them. Now, it's worth noting that those other stresses are the leading driver of ecosystem loss today. So climate change matters today and may become the dominant factor in the future, but land use, pollution, overuse, exploitation, fishing, and so on, these are the leading drivers of ecosystem loss today. So we can do a lot, but relative to those climate change impacts, there's little we can do. So as a result, there's going to be considerable suffering. We can't adapt our way out of this problem. Even if emissions cuts are very rapid, we're going to see a considerable increase in climate impacts. So is there something else we can do? Well, it's not a plan B, but we might be able to do something. So here is a nice GIF of the recent Hunga Tonga eruption, one of the most powerful explosive eruptions caught on, I guess it's a geostationary satellite. And this figure here shows the plume of sulfur dioxide that was emitted by the eruption. Now, sulfur dioxide is very important for the climate because it goes on to react to form sulfuric acid. And sulfuric acid very readily forms very tiny droplets that are very good at scattering light. So you have an eruption here, it emits, I think it was 400,000 tons of sulfur dioxide. This goes on to form very many tiny little droplets that will scatter light and cool the Earth a little. Now, most eruptions are much smaller than this one. They emit material into the lower atmosphere. This is a plot showing clouds and then the volcanic plume as a function of longitude and then altitude. And the key difference here is that this boundary between the troposphere, the lower atmosphere with weather and clouds, and the stratosphere, the stable layer of the atmosphere above it. Now you can see the volcanic plume reached into the stratosphere. Now this means it's got above the clouds that will pull and scavenge those particles out of the air. And so they're going to last a lot longer up there than they would in the lower atmosphere. Now, the Honga Tonga eruption is pretty small. 400,000 tons is a lot of stuff, but it's relatively small compared to these other eruptions that happened through the 20th century. Mount Agung, El Chichon, and Mount Pinatubo all produced a much larger observable cooling. So this is global mean temperature over time. And the red line effectively cancels out the effects of El Niños and La Niñas. El Niños make the world warmer, La Niñas make the world cooler. If you iron those out, you can see the effects of these eruptions more clearly. They cool the planet for a few years. A couple of years, temperatures drop by a few tenths of a degree. Now, each of these eruptions put in 10 megatons odd of sulfur dioxide, so much more than Honga Tonga did, and they produced this cooling. And one of the reasons they had such a big effect is they were, I think most of them were in the tropics. So what happens here, like you were seeing in the other picture, the eruptions are explosive enough to put the particles into the upper atmosphere, into the stratosphere. And what's illustrated in this figure here is the circulation. So you can see that in the tropics, there's a circulation pattern that pushes the particles up and then distributes them to the poles. So these tropical eruptions, they happened in one place in the tropics, produced a global aerosol layer that then scattered light and cooled the whole planet for a year or two before gradually falling out and cleaning out the atmosphere. There you go. Now, stratospheric aerosol injection is effectively the idea that we could mimic this cooling effect. Now, we wouldn't trigger volcanic eruptions. We would use high-flying jets to deliver millions of tons of sulfur dioxide or other particles up to the stratosphere. Now, to get up that high, you need to fly about 20 kilometers up, 60,000 feet. Most aircraft do not do this. That's because they don't need to do this. It's perfectly possible. It's difficult, but it's perfectly possible. And all the engineering assessments have concluded that you could do this with existing technology, existing engines, and so on. But with a new design of an aircraft would be needed. And someone has gone ahead and designed that. This thing would be about the size of a 747. Its body is a bit narrower. Its wings are a bit thicker. It's got more engines, but it's a plane. We know how to build these kind of things. And for a few $1 billion, it could be designed, built. And then basically to deliver 1 million tons of material to the stratosphere would require 180 flights a day, which could be done with 60 aircraft. And they reckon this could be done at a cost of $1.4 billion per million tons per year. Which means that offsetting about 1 Celsius of warming would cost only tens of billions of dollars per year. Now I say only because tens of billions of dollars is obviously a large amount of money, but only because it's relative to the trillions of dollars it's going to cost to transition to a cleaner energy system, and the many trillions it will cost to cope with the impacts of climate change. This is relatively cheap and could have a very substantial effect on the climate. However, cannot solve climate change. This is not a plan B. So, as I'll talk about in the next section, it cannot perfectly offset the effects of climate change. It isn't anti-CO2, it's a different effect on the climate. And it only masks the warming. So the CO2 and other greenhouse gases will remain in the atmosphere, and CO2 will persist for hundreds and thousands of years. So this would cool the planet, but as I mentioned with volcanoes, the particles fall out after a couple of years. So you need to continuously re-inject to keep the cooling effect. So you don't deal with the underlying cause, you're dealing with a symptom, an important symptom, but only a symptom of the underlying problem. It masks the warming. Now, it would mean that the direct effects of CO2 would persist. CO2 affects plants, it makes them more productive. It also makes them more water use efficient. That's not all good news. It leads to increases in river runoff in wet places and potentially decreases in dry places, because if the place is so dry that plants struggle, and now plants are more water use efficient, you get more plants, they capture more water, and there's less water to run down rivers in dry places. There's also ocean acidification. Now, there's not really an upside to this, but it's dissolved as CO2 dissolves in the ocean. It changes the ocean's chemistry, and it makes it harder for shell-forming creatures to form their shells, with impacts on the ecosystem. And it has a number of side effects, which I'm about to go through. So first, to scatter light to space, you'd have to scatter light. Now, when these little particles that you'd add to the atmosphere don't just scatter light straight back to space, they also scatter it downwards. You'll have all experienced this. A hazy day, that's because there's small particles in the air. They're scattering light up to space, which cools the surface a little, but they also scatter light down. The sky appears grayer. Now, the three images here are this is very preliminary stuff. This is a very approximate picture of how it might change the sky. So from the top is a completely clear sky, like desert clear, and then down one notch is a simulation of an aerosol layer that's perhaps large enough to produce a significant cooling. This is stuff, we've got a paper in the works on this, because it's quite hard to work this out, but it would make the sky appear hazier. How much hazier is a question that we're looking into now. And it would add to the acid rain problem. Now, sulfur dioxide is a poisonous pollutant that's emitted as a byproduct of burning coal and oil and other things, and the volcanoes emit it. And you can see here, this is, it also causes acid rain. This is a forest. I'm not sure it's Canada or Scandinavia, but those are the two regions worst affected. You can see it's full of dead trees that were killed in the 80s or so, but they're young trees growing up. This is because the sulfate pollution problem peaked in 1980 and then declined globally. Now, it declined much more in developed countries. It's down about a quarter from its peak, whereas it has increased in developing countries. So yeah, sulfate pollution is an existing thing. It's ongoing, and adding stratospheric aerosol geoengineering, stratospheric aerosol injection would add to this problem. We're talking somewhere in the ballpark of 10 million tons of material would be needed to have a significant impact on the climate. So it would add about 10% to the existing pollution problem. Another important side effect is it would delay the recovery of the ozone hole by decades. This is a picture of the ozone hole. So you can see here Antarctica. It forms every year in the winter, southern hemisphere winter, over Antarctica. It only forms there because you need the ice crystals that form in the very cold stratosphere over Antarctica to catalyze the chemical reaction. The CFCs are the driver, but you need those ice crystals for the reaction to occur, and they only form really over Antarctica, which is why the ozone hole's there. So this plot is, in purple, is observed ozone trends over Antarctica. You see they dipped, reached the minimum in the late 90s and have sort of been bouncing up and recovering. And then in black is a projection, there's a climate model simulation that shows the same thing. And then into the future, you can see the ozone hole recovering. In blue, it's the same simulation. It's a high CO2 scenario with stratospheric aerosol geoengineering applied at a very large scale to offset, I think it's 3 or 4 Celsius of warming. And what you can see is there's an initial drop in the ozone layer over Antarctica, and then it slowly recovers. So it delays the recovery of the ozone hole by decades. So taken together, this is not a replacement for emissions cuts. We can't just replace emissions cuts with this. This is not a plan B. But could it be part of plan A plus? So what would that look like? This is an illustrative figure. Global mean temperature on the y-axis and year on the x-axis. So from the year 2000 out to 2200. So here we go. Here's roughly how temperature might evolve in a world without climate policy. Temperature might rise by 3.5 Celsius. Illustrative stuff here. Now with emissions cuts, if we drive CO2 emissions and other greenhouse gases to zero, we're only going to stop the planet from warming. It's not going to go back the way it was. It's not like air pollution where you clean it up and it's gone. In this case, the CO2 hangs around and it has a residual effect that will last thousands of years. So if we eliminate emission CO2, we will just stop the planet from warming. It'll slowly, over the course of centuries, come down, but only very slowly. Now, negative emissions technologies or carbon dioxide removal, adding that will allow you a way to drive CO2 and then temperature down. Now, this is an illustrative figure, and perhaps I've shown this coming down a bit too steeply. This will be very hard to implement at large scale, and it might take even longer in the 22nd century to clear out the residues from the industrial emissions. But this is just illustrative. Now, where stratospheric aerosol injection comes in, well, that's plan A, and plan A plus would be just to do all of the above and apply stratospheric aerosol injection to say to limit warming below 1.5 Celsius. So in my illustrative case, temperatures would have peaked about 2.5 and then come down below 1.5 only in the late 22nd century. Now that is what we'd have got without SAI, and with SAI, in this case, I'm offsetting all warming at above 1.5 Celsius, and then we turn it off once CO2 and temperatures fall back below that level. So how would it look? This is results from a relatively recent study where they did a sophisticated representation of this idea. So volcanoes throw sulfur up where they do, and it ends up more or less a global distribution. And we could do the same thing. We could throw it up on the equator and we get an aerosol layer that covers the planet. But we can be smarter than that. And that's what they did in this simulation. They aimed to, as evenly as possible, restore temperatures across the world. So they injected aerosols at different latitudes and then tuned those deployment so that temperatures were as even as possible. So they best offset the global mean temperature change. Now, what we're showing in this plot is here is the pattern of change that we expect with 1 Celsius of global warming. And then on the right is the pattern of change we'd expect from 1 Celsius of global warming minus 1 Celsius of stratospheric aerosol injection. So you've got no net temperature change, but it isn't perfect. And you can see that here. So on the left first, you can see the pattern of global warming is that the tropical oceans will warm less than the rest of the world. The land will warm a bit more, and the high latitudes in the northern hemisphere will warm especially more than that. So parts of the Arctic are warming 3-4 more times faster than the rest of the world. Now on the right, you can see the effects here. It's worked very well. Most of the world is white, as in there's less than 0.2 Celsius of warming or cooling. Now there are some patches that are a little bit cooler in blue here, and some patches that are warmer than they were, but a lot cooler than they would be under the case of global warming. So what we can say is it works very well for temperature change. This is robust across all the different model simulations. Most of the world would be within 10, maybe 20% of the trend. So you can see here, though, in the high Arctic, maybe we've got 0.5 degree Celsius of warming residual relative to the 2 or 3 Celsius we'd see under global warming. We've only offset a quarter, but it's still, 3/4 of the warming has been offset. Here's the same thing for rainfall. So here's the pattern of change under global warming we expect. Some places get a lot wetter, some places get a lot drier. And here is the change with SAI. And here you can see that the overall brightness, the saturation of the picture is much lower. The changes overall are smaller, but you'll notice it tends towards the orange. That means it's getting drier in more places. But overall, the magnitude of change is substantially reduced. But some places definitely have less rain than they would do under the climate change scenario. Now, this last one is water availability. So this is rainfall minus the effect of evaporation. Because if you've got less rainfall, but also less evaporation, you might have no net change. So again, for global warming, we can see a similar pattern too for precipitation. Generally dry places tend to get drier and wet places tend to get wetter. That's not universally true. And there's large magnitude changes overall. And on the right, again, we see smaller magnitude of changes, but it's a mixed picture. So let's pick out a few places. Most places see less change. That's quite clear from this figure, but there's a couple that stand out as seeing potentially more change. The northern Amazon region here is a little more orange here than it is there. West Africa, perhaps, this gets wetter here, gets drier here. And India, it's getting wetter under climate change and getting drier here. So overall, we're seeing a reduced magnitude of change, but some places will see a greater change or a different change. So I reanalyzed that same data. And what I did was a simple test. Was the magnitude of climate change in a particular location made bigger? Did it go from a 5% increase in rainfall to a 7% increase in rainfall, or a minus 7%? That would be, come on to the side here, the climate change increased, or did it reduce from 5% to 3% or minus 3%, in which case it would be blue. So for temperature and extreme temperature, we found every single place on Earth would see the effects of climate change significantly reduced. I think this is true in every simulation. Now, water availability, rainfall minus evaporation, we find that about 1/3 of all places see the effects of climate change significantly reduced, and about 9% see the effects of climate change increased. So this might be a small positive trend that becomes a larger negative trend. You'll notice the number doesn't add up to 100. This is because some places the effects are too small to be statistically significant. We don't know whether it was just noise or whether it was an actual signal. so they're not counted. And then we looked at extreme rainfall, so the wettest period in the year. We find that stratospheric aerosol injection reduced in 2/3 of the world the effect. In 2/3 of the world, SAI significantly reduced the change in extreme precipitation and only increased it in 1 and a bit percent. Now, this is a rather complex figure, so let me just focus in on the one on the right here. What I'm showing is I'm grouping the results by the magnitude of climate change. So as you go here, this is no change in extreme rainfall under climate change, and then red are places that see a greater change with SAI. Now, as we go off to the right here, these are places that see very large increases in extreme rainfall. And using the same color as before, dark blue shows the fraction of places that are seeing significantly less climate change. So basically, as the effects of climate change got larger, SAI was more likely to reduce those changes. So it basically makes things better in places that see the greatest changes and may make things worse in places that see the least change, places that are sort of centered around zero. The same kind of thing holds for water availability. You can see that the places that see greater change concentrated in those areas that saw the least change under climate change, whereas the places that see the greatest change were almost certain to see those reduced significantly. So the larger the effects of climate change, the more likely they are to be reduced by SAI. So I'll also start wrapping up now. The IPCC's report had a list of 35 climate impact drivers, which is a lot, but these are the things that they keep an eye on, the physical changes in the climate system that we're worried about. Now, they group them into different categories: heat and cold, wet and dry, wind, so on and so forth. And I'm going to do a similar grouping together and just quickly run through the likely effects of SAI and where I think things stand. So heat and cold, extreme heat, rises in temperature and so on. Extreme heat is going to be reduced. It's effectively certain it will be true universally, but so would extreme cold. Now, that's a benefit of climate change. Extreme cold kills people. And as the planet warms, we get less extreme cold. There might be some exceptions. No, so generally it would be highly effective at reversing both the harms of extreme heat and the benefits of less extreme cold. Now, heavy rains, as the planet warms, as the air warms, it carries more moisture. And that means that when you get a storm, there's more water being carried by the clouds, and it can dump more out at once. This is a very robust result that for every degree Celsius of warming, we get 7% more intense rainfall. And as we lower temperature with SAI, we are effectively certain to see the reverse of that. Now, it won't be exactly true in every detail in all regions. I found 1.3% of the world saw a greater change, but 2/3 of the world saw that significantly reduced. So it's highly effective in general at reducing heavy rains. Then there's rainfall aridity drought. Now, it's mixed. It's going to be effective in many places. I found 36% of the world saw the change in water availability reduced, so it's less different with SAI than it is with climate change. But some places will get drier or see greater change. So it was 36% saw a significant reduction and 9% saw a significant increase. So the effects are mixed. I've gone for orange here, maybe light green, depending which region you're in. Now, there's limited work on storms. I was involved in a paper where we used a very high resolution model and we directly simulated tropical cyclones. And we found that under climate change, the overall intensity of tropical cyclones increased substantially. And if we halved future warming with solar geoengineering, we reduced that intensification of tropical cyclones by 85%. So even though we'd offset half the warming, we'd reduce the storm intensity by 80%. So I put it blue here because I think there's some big uncertainties. It hasn't really been looked at in great depth, but I think there's good reason to believe that it should be reduced, or the effects of climate change should be offset there. Snow, ice, permafrost. These are all melted as the planet warms. So all the work we've got so far suggests that if you cool the planet, you're going to reduce the amount that snow, ice, and permafrost melt. It's fairly straightforward. And as a result, it's also going to be very effective at offsetting sea level rise. I've published a few papers on this, but it's fairly straightforward. Land ice in glaciers and ice sheets, again, is melted at higher temperatures. So if we reduce temperatures, we're going to get less melting of the ice sheets. And the other contributor to sea level rise is the thermal expansion of the oceans. As the oceans take up heat, they warm, they expand. If you cool the planet, they will warm less, they will expand less. So it's going to be highly effective at reducing sea level rise. Stopping sea level rise is another matter. The ice sheets have got their own internal dynamics, and they are going to be melting for millennia. If we keep temperatures at today's levels, we would see sea level rise continuing for hundreds and thousands of years. So it's going to be very hard to stop, but it would be highly effective at reducing sea level rise. Now, ocean acidification is another key concern. And SAI would be largely ineffective. It doesn't really do anything for CO2. The CO2 will still be there. Much of it will go in the ocean, and it won't really do a great deal. It will have some effect because permafrost, as it melts, emits CO2. And as the land surface warms, it's going to become less good at holding on to the carbon it has. So there are some positive climate carbon feedbacks that add more CO2 to the atmosphere that we can expect to be reduced. But this is relatively modest compared to the fact that basically the CO2 is still there. And then there's marine heat waves. The Great Barrier Reef, I think 2/3 of it was bleached in 2016 because there was a marine heat wave. Now that's driven by temperature. You lower temperatures, these are going to become less intense. So again, it's going to be highly effective at offsetting these changes. So taken together, basically many climate changes are going to be reduced either universally, heat, the melting of ice, sea level rise, marine heat waves, or nearly universally in the case of heavy rains and storms. Not totally sure what's happening there. But there's a couple of things that could get worse. Obviously, extreme cold. If your country or region benefits from warming, you're not going to benefit if that warming is offset. And rainfall aridity and drought. Some places will see changes in hydrology that are not beneficial. Now, that will be a relatively small fraction of places. Actually, there's a 4-to-1 ratio between places that saw a significant reduction versus a significant increase. And even in those places that see a significant increase, so say India, we saw a drying, they will also see reduced temperatures, reduced heavy rains, less melting of the glaciers, and less sea level rise. So it's kind of an open question, like, would those regions be better off despite the fact they will face a different hydrological hazard with this? We don't know, it's early days yet. So that was all assuming it kind of goes as I've outlined, plan A plus. It's exactly, we do everything we can on plan A, and then on top, we do stratospheric aerosol injection. But one of the main concerns with this idea is that developing it, even talking about it, could deter mitigation. So here's that same figure I showed earlier, global mean temperature, cumulative CO2, and I've just sort of plotted on here an illustrative scenario that leads to a little over 2 Celsius of warming. Now, adding SAI means we're going to decouple global temperatures from CO2. We can drive temperatures down independently of CO2. Now, there's a worry that could lead to a delay in emissions cuts. You could get, it's often called the super Freakonomics pivot. There was a book, Super Freakonomics, where these economists said, well, look, it only costs a few $1 billion per year to do SAI. Therefore, let's not spend trillions of dollars changing the economy. Let's just do $10 billion there, problem solved, easy peasy. That's the fear. There could be this switch here. And what you then, in such a scenario, would end up with is you'd aim to lower temperatures to 1.5 Celsius from where you think you were going, but actually you get more CO2 emissions. And so you end up in this dark blue case. So, you're comparing, instead of this orange case against this light blue case, you've got to compare the orange case against the dark blue. Now, the magnitude of this effect is really uncertain. There's even some suggestions it might be negative. The idea of stratospheric aerosol injection is quite frightening. And many people, I've personally was at an event or two, and there's been various efforts to elicit responses from the public. And many people seem more willing to act on climate change after hearing about this idea. But that's not the end of the story. So it's uncertain, but this is the concern. Now, of course, even worse than deploying SI, it working, and you getting slightly more emissions would be if you think SAI is going to work and it leads to a delay in emissions cuts, but then it never materializes. And you think you're going to get this blue case, and actually you get the red case. So that's one of the big worries with this. So to reiterate, plan A plus. SAI offers a means of offsetting the warming effects of greenhouse gases. Used as a complement to emissions cuts and negative emissions technologies, it may greatly reduce climate risks, potentially in all regions, but that would be a matter of balancing various risks against one another. Now, significant uncertainties remain. I've been working on this for a decade or so. There's relatively few of us who've looked at this in depth. There's, I think, yeah, only a fraction of the effort that's gone into projecting the effects of climate change has gone into projecting the effects of SAI. So this is pretty preliminary, and I think my judgment on this is correct, but there are others who are much more cautious about the potential benefits and risks and are put much more emphasis on the uncertainty. So I want to stress that my take is not universally accepted, and there are big uncertainties around the effects of this idea. But developing and deploying SAI would only add less than 1% to the cost of fighting climate change. Tens of billions of dollars compared to the trillions of dollars of needed for emissions cuts and negative emissions technologies. Now, today we're only spending maybe $10 million per year globally researching this topic, and £0 per year. The UK has no research on this topic. But yeah, the money there will be actually building the aircraft, running the system, putting up satellites, the expensive stuff. So plan A plus, in my mind, is devote 100% of your effort to plan A. Cut emissions as quickly as you can, develop negative emissions technologies. And if we can stretch to 101%, that extra 1% might make a really big difference. It could greatly reduce the risk of climate change. But we need more research to know if that's the case. So yeah, plan A. I'll give you a little quick run through of that. Emissions cuts and negative emissions technologies are the plan, but what we are planning to do is not enough to limit warming below 1.5 or even 2. Adaptation will help and is very important, but it has its limits. So there'll be considerable suffering in the future, even under rapid emissions cuts. I explained stratospheric aerosol injection, SAI, is feasible and relatively cheap, but it's not a substitute for emissions cuts. It has various side effects. It doesn't fix the underlying problem. It's not a plan B. But used as a complement to these other efforts, it might greatly reduce the risk of climate change. That's plan A plus. So I'm going to quickly end a little bit of self-promotion. We've got a new climate podcast, Jesse Reynolds and myself, and we've talked to a few people already. We've got a couple episodes out. Neil Stevenson, sci-fi writer, has written a book on termination shock, called Termination Shock, about solar geoengineering. And Elizabeth Kolber also talks about that. We recorded an episode with her. She's a Pulitzer Prize winning author who wrote Under a White Sky, which touches on solar geoengineering, but also a range of other radical environmental technologies. So thanks for listening.
Thanks very much, Peter. That was really interesting. Yeah, I'm just going to just do some quick announcements and stuff while people before they dial off at the end of the session. But just to make sure, guys, do put your questions in the Slido. I see some people have put some things in the comments on YouTube. If you can just stick them in the Slido instead, that'd be really useful. And upvote some of the questions that are already in there so that we can more easily filter through them. Also, if you're not already in the Climate Hub and you're a public servant in the UK, then please get on there. And if you are on there, but you're not going on there very often, please just jump on there a couple of times a week and see if there's anything interesting or anything you can help out with, or any questions that you want to ask the community. We're centered around kind of well-being, knowledge sharing, collaboration, and any more cross-government working we can do would be, a great way to build more resilience and ambition and stuff within the public sector on climate and biodiversity loss. We'll teach you how to use the platform if you don't know how to use it. We're going to start doing live sessions like once a month again, so people can dial into those to learn how to use Slack properly. And also, size and growth matters. So we really do need people to, bring like colleagues and share our resources and access to our platform so we can get as many people on there. And the more new blood we get coming on there, they do tend to help the platform work more fluidly. So yeah, share our resources. The link tree is in the show notes of this as well. Check out our resources if you haven't looked at them already. You're on our YouTube channel by watching this video. So check out some of the stuff we've got on there as well. There's loads of great resources out there, and we've got some of them listed on our channel as well as some of the past events that we've done. We've got a bit of crossover with Peter. He did an interview with Holly Jean Buck very recently in this podcast, and we had her as one of our first sessions that we did of this a couple of years ago now. So do have a look at that. And we've now got a jobs board that we're promoting. There's a lot of jobs coming through the public sector now that are on sustainability and climate change, and our community is kind of capturing them. We're putting them on our jobs board as well as volunteer opportunities as well. So, do have a look on there if this is a sector that you're looking to move into as well. And there's also a feedback link underneath the YouTube video as well in the show notes. So feedback on what you think of the event, and if you've got anyone that you think or any areas that you think we should cover or get someone to talk about, then please do that too. I'll just try and get through as many of the questions as we can. We've got quite a few, so if we can just keep the responses as brief as possible, Peter, we'll give that a go.
I'll just add a quick thing. You mentioned I noticed that you had Rupert Reed on in your last session. I had a debate with Rupert Reed. People might be interested in looking up the Institute for Environment and Engineering and Technology, the IET. Yeah, Rupert Reed and I had a debate on this idea, the stratospheric aerosol injection.
Yeah, thanks for reminding me about that. Actually, that does sound really interesting. It sounds like your tack on things is you're slightly more optimistic about things than a lot of other people are, certainly within our community, I'd say. And there was an interesting point that you made about one of your colleagues' research on Twitter, about academics on Twitter. Was that earlier?
Oh yes. Yeah, unpublished, but I think a survey of academics, people who know about the climate problem, and she found that amongst those, if you asked them how doomed, I'm not sure exactly what the question was, how doomed they thought we were, the more time they spent on Twitter, the more they thought we were doomed. So the correlation was not with expertise on the topic, but with how much Twitter you follow. So my Twitterverse isn't the real world.
Yes, that's a really important thing to remember too. So I'm just going to start launching into some of the community questions. There's one here about Arctic amplification from Robert Tulip, just saying, given the urgency of that issue, is it a good idea to try and focus on regrowing the Arctic sea ice and the Arctic ice before we look at other things? And also there was a question about marine cloud brightening. I think that's a course of action to have an effect in the Arctic, if I'm right.
Yes. So yes. So I focused on stratospheric aerosol injection. There's basically two big ideas for solar geoengineering that look plausible. Stratospheric aerosol injection creates a global aerosol layer. We can't control the fine details, but we can control broadly, is it thicker at high latitudes or thicker at the tropics? Or is it limited to high latitudes? I'll talk about that in a second. Marine cloud brightening is an idea to increase the reflectivity of clouds in certain patches of the ocean. So there's patches near Australia, near California, relatively limited. There's some suggestions it might be applicable in the Arctic and other places, but there's been, I think, one study that it might do something. It's pretty preliminary work there. So yeah, marine cloud brightening might work, but it's quite regional. It's quite different in character from stratospheric aerosol injection. Now, I focused on global stratospheric aerosol injection, and that requires getting into the tropical stratosphere. And the tropical stratosphere is 20 kilometers up, but the mid-latitude stratosphere is a lot lower. It actually, if you fly from the UK to New York, you'll pop up into the stratosphere. That means existing jets, ordinary aircraft, can get to an altitude to release stuff in the mid-latitude and high-latitude stratosphere. This means you could do stratospheric aerosol injection in the Arctic with existing aircraft. You could repurpose some of these military refueling jets, for example, and apply stratospheric aerosol injection that way. So for that Arctic application, there effectively is very little barrier to entry. For global deployment, you've got to justify spending billions of dollars developing this aircraft, which presumably means you want to have spent billions of dollars doing the research to make sure it's a good idea first. But for the Arctic application, you don't have that barrier, or don't have nearly as much of a barrier. Now, there are some motivations. The Arctic is warming a lot faster than the rest of the world. There are these positive feedbacks. As the ice is lost, the dark ocean is revealed and more sunlight's absorbed, amplifying warming. And the permafrost melts. And as it melts, it emits CO2 and other greenhouse gases, and that adds to global warming. I should say that it's sort of, I think the worst case scenario for permafrost is somewhere in the ballpark of adding 10 to 15% of the effect of humanity. So it's a big addition, but it won't dwarf humanity's contribution. It will add to it. So there's some motivation for doing it. And the other idea might be that because it's only the Arctic, there's only really a concern of the Arctic nations. Now, I don't think that holds, because if you just cool the Arctic, you're not going to have effects just in the Arctic. If you cool one hemisphere and not the other, you actually get a shift in the tropical rain belts. This is something that's very widely established. Like, if you just cool one side of the planet, if volcanoes go off and just at high latitudes, they'll mainly cool one hemisphere. And what happens is the rain belt, the monsoons, the tropical rains, shift towards the warmer hemisphere. So if you cool the northern hemisphere, you'll get a shift southwards. So some of the Sahelian droughts in Africa are correlated with big eruptions that focus in the northern hemisphere. So yes, there are some reasons to focus on it. I've got a PhD student who's going to be looking at this topic, but there are some reasons to be careful. It's not necessarily an easier, simpler first step. It will have global implications. They just won't be as large.
I'm sure that governments can come up with some way to spend more money on, aircraft that can be used for other things as well, I'm sure. But one question here is from someone who's just remained anonymous, is just talking about how much more research do we need before we feel we could be confident in the impacts of what these are, and us actually being able to use it in a useful way.
A lot more. I mean, I think a good ballpark is that kind of, if it's going to cost, let's just say, $2 billion to design and build an aircraft that could do this, we want to have spent, more than that, making sure this is a good idea. And of course, the bigger concern is not how much it would cost to do it. It would be, what the consequence would be. Now, there's a kind of analogy to the early stages of climate change. We still don't know the full impacts of climate change and all its we can't perfectly predict all the effects of climate change, and we never will be able to. And even back in the 80s and 90s, we already knew enough to warn us off emitting CO2 indefinitely. Even if climate science didn't advance beyond the 1990s, we'd still know enough to say, right, we shouldn't just keep emitting CO2 forever. So I think it's a challenging one. There are some big uncertainties remaining that really need to be nailed down. For example, when we simulate stratospheric aerosol injection, we just put the aerosols into the grid boxes of the models. The models are sort of pixelated. And so we just add the aerosols to a whole large grid box, like 100 by 100 kilometer block at once. But in reality, there'd be a narrow plume that comes out the back of your aircraft. We need to simulate the evolution of the particles in the plume, how that would sort of noodle around through the stratosphere and then eventually spread out. That's a gap in our understanding, a gap in our capabilities that needs to be addressed. And I mentioned the simulation that I was analyzing and showing, that's been completed in a single cloud model. And we can't rely on a single cloud model to make our projections. For climate change, what we do, we know all the models have their limitations and their flaws. They'll never be perfect. But what we have is like 20 or 30 different cloud models that together project a range of responses. And we can be pretty sure, we have more confidence that the real world is going to be somewhere in that range than if we just relied on a single model. So we've got new capabilities to add to represent this stuff realistically. We've got to bring in a broader set of models that are able to simulate it realistically. So not just one or two, but we need 20 or 30, the whole global community to be looking at it. And then off the back end of the climate model simulations, there's all these impact model assessments that are needed. So agricultural models and so on. Basically, you'd want to replicate what we do for the IPCC report for climate change. It's huge effort, thousands of scientists assessing these scenarios. Replicate that for stratospheric aerosol injection. That's a big effort. And yeah, so I think it's decade, 2 decades out at least in terms of the analysis and so on required. If we start focusing on this and doing the work.
And going on to the other major issue, someone's asked a question about the global governance of this. Obviously, that's a really sticky point, isn't it? If we did use it.
Yes. So stratospheric aerosol injection would have global consequences. I didn't stress this enough, perhaps, but you couldn't just create an aerosol pocket that floats over the UK and only cools the UK. The wind in the stratosphere, I guess you saw the initial part of that, Hunga Tonga, the eruption went off, and already a few days later, you could see the plume had traveled westwards around the world. So wherever you inject the aerosols, they whip around east-west, all the way around the world, and then gradually are pushed towards the poles. So you could create an aerosol layer that's concentrated in the Arctic, you could create an aerosol layer that's global, or that's thicker at high latitudes, thicker in the tropics, but you can't create one that's just cooling China. So this is something that would inevitably have global consequences. And yeah, so in a way, for it to be legitimate, there has to be some degree of involvement of the global community. How that could be done, what would be the right way to do it, this is a very challenging thing. And what would happen if some nations got together and just did it what would it be able to do to stop them? It's hard to know how this will pan out, and we can imagine better or worse scenarios. But yeah, it's a real big question, and it's one that a lot of the work is focused on.
Yeah, and as you're saying, there's different effects in different parts of the world, and different countries could act on their own or with, as you say, in an aggregate. But then it would be difficult to prove whether they'd had a negative impact on another country, wouldn't it? So if they did try to take them to task over it, saying that you'd caused this drought for us, then it would be really hard with attribution.
Yeah, attribution will be a big challenge with this. And it is with climate change, like knowing how the climate has changed and whether this drought or that event was sort of natural or what role climate change had in it is difficult. And it'll be equally difficult or more so with if you start deploying stratospheric aerosol geoengineering. Now, in a sense, for it to stick, to say, oh, this drought that I'm experiencing in India is definitely due to stratospheric aerosol geoengineering, you'd have to be sure that it wouldn't have happened under climate change. And it's difficult. We're going to have to rely on models. We're going to have to observe for decades to see the trends. Yeah, it's going to be a challenge, but I think it's going to be difficult.
One of the other questions here is, what about the impact that acid rain would have on the ecosystems in terms of their ability to sequester carbon? Have you looked at that at all?
I don't know if that's been looked at all. I think what has been done is people have looked at the relative effect of historical acid rain problems versus the problems that you'd get with SAI. Now, it's worth making something clear. Ocean acidification is driven by the tens of billions of tons of CO2 that we add to the atmosphere every year. It forms a weak acid, but there's a hell of a lot of it. So that's what's driving ocean acidification. Acid rain doesn't really affect ocean acidification, but it does affect effectively high latitude, cooler regions, effectively the forests and lakes that sort of slowly recharge. The acid rain, the acidity accumulates there, and that's what leads to these harms. Now, I think people have looked at this and, a 10 million ton deployment of stratospheric aerosol injection is only 10% of current emissions of sulfur dioxide, but it'd be distributed differently. Now, it would mainly come down across the high latitudes and would be quite diffuse, whereas the historical problem and the current problems with acid rain are quite concentrated. If you're downwind of Beijing, you're going to have an acid rain problem that's very large today. Whereas, Scandinavia and Canada were downwind of the European and American pollution centers. They were the regions that suffered the greatest harms of acid rain historically. So it would have a modest effect relative to historic impacts in places historically impacted, but it will also affect areas that were largely unaffected historically. I think it needs to be looked at in greater depth, but I think it also needs to be put in the context of these historical pollution problems.
Just a question from me. Can you envisage a future where we don't use this? Do you think it's inevitable that we're going to use it?
No, I mean, I think that the future's open. I mean, I think my view, climate change is sort of it's a sliding scale of badness. As the planet warms, things will get worse incrementally each year. It's going to be hard for there to be, yesterday everything was fine, tomorrow is now an urgent crisis and everything needs to change. Now, there'll be local regions where that kind of political flip happens. I mean, the world already declared a bunch of climate emergencies, but they didn't really do much. I think the same thing will be true here. We could just, year by year, get closer and closer to 3 Celsius, and just this idea just forever seems too radical and never gets developed. And that's possible. But if the evidence continues to suggest that it could greatly reduce the risk of climate change, I think this is something we should investigate. And there is a risk that, the nations that are more on the front line of climate change, I'm thinking particularly of India, but also China, they're much more exposed to climate change than we are. They are very powerful. India is going to be the 3rd largest economy in the world, if it's not already. And they would have more of the moral authority to sort of go ahead and do this and say, we're acting on responsible, in favor of the most vulnerable. So I think there's a risk that it could get developed and deployed unilaterally or by nations that feel vulnerable, that are going to be more and more powerful in the future. So I think the more that we understand and explore this and point out its flaws, understand its limitations, explore its benefits and how it could be managed, the better position will be to either reject or develop this as time goes on.
If it was rolled out, is there potential for it to be used to try and achieve greater cuts in temperatures than 1 degree, or would that start to move into the negative impacts more?
There's effectively no limit to the amount of cooling you can do. So you could drive temperatures back to the pre-industrial, even under a scenario that the world was warming 4 Celsius. I mean, the more that you do, the larger the side effects and impacts will be. The bigger the ozone loss, the more acid rain, the more. I mean, I showed the climate signal for 1 Celsius of warming in this, 1 Celsius of warming offset. If that was 5 Celsius of warming and 5 Celsius of warming offset, the trends are going to be larger, the differences are going to be larger, the impacts are going to be larger, ocean acidification is going to be larger. But yes, you could go further and drive temperatures down, and there might be motivation to do so. Halting temperatures will halt climate change, but sea level rise is, even at today's temperature, even if we fix temperature at today's value, the Greenland ice sheet is slowly destabilizing. Parts of West Antarctica are destabilized, or seem to be. We're going to get meters of sea level rise in the very long run, even if we keep temperatures steady. So there might be motivation to drive temperatures back down. But that would be to really trust this technology and really trust that we can manage this in the long run, which I don't think we're in the position to make those kind of promises or projections at the moment.
Are there any other chemicals that could be used instead of sulfite aerosols?
Yes. So sulfates are the devil we know, because volcanoes release them, and we've been able to observe their side effects, impacts, how it works. And we know that it would work. We know it would have side effects, but we roughly know their scale. I mean, 1991, the sky wasn't completely white. I mean, that was Mount Pinatubo. It wasn't that the sky turned completely white. I think we'd remember. It wasn't that the ozone hole, ripped right open and the whole world got skin cancer. I'm being a bit silly there, but we've got that historical example that tells us the scale of this thing. It has downsides, sulfates, and there are alternatives. Calcite is another particle, alumina, diamond dust, which apparently isn't as ludicrous as it sounds, but there are these proposals for alternative particles that might avoid some of the side effects and might work better, but they're more uncertain. We don't have experience of adding millions of tons of calcite to the stratosphere. So we'd need experiments and field tests and careful study to understand the impacts it would have on stratospheric chemistry. So the advantage of sulfates is we know it, even though it has these downsides.
We've got a question about it being weaponized effectively. Yeah, I suppose that's one of the things that attribution is so difficult. It'd be a really kind of stupid idea to roll it out in that kind of way at this point.
Yeah, I mean, I think unless your enemy was the entire tropics, you've really not got very many options. You can't. I mean, I guess yeah. If Russia wants the world to be warmer, then cooling the world will go against their interests. Sure, but because you can't target this in a way, you can't like steer hurricanes. It's not something you can only adjust the pattern of cooling over the course of years. So you can't directly change the weather with this technology. So, and you've also got very little spatial control. All you can do is, the worst you could do, the most harm you could do with this is to cool just the northern hemisphere, which would shift the tropical rain belts dramatically to the south and would screw over, the tropics. But, there's no sense in trying to harm the entire tropics if you're only at war with one nation. I think it's kind of implausible to use this as a weapon. You can imagine that whoever is deploying it might deploy it in their interests and not in the interests of others. But that isn't the same thing as weaponizing, like causing deliberate harm targeted to a particular region. That there's limited options for doing that.
In terms of the timescales about being able to get that mass of sulfate aerosols into the atmosphere, how long would it take to, I don't know if you covered it in your presentation actually, but how long would it take to give, a degree of cooling, for example?
I mean, yeah, so I mean, it's probably worth looking at the volcanic eruptions. You wouldn't want to do it like a volcano. The volcanoes put up 10 million tons in one day, or in a few weeks. Then that eventually fell out, but you get this rapid cooling in the first year or two. And if you kept that up, you'd get a rapid cooling initially that would then sort of slow, and you would offset temperature, substantial amount of temperature. You wouldn't want to do it like that. You'd want to phase it up gradually so that you'd say either keep temperatures constant or slowly decline. So you'd want to scale it up. Also, it would be quite dramatic to go from, we don't know this idea is going to work, to really rapidly scaling it up to try and drive temperature back to the pre-industrial. I think the wisest course would be, if we're getting quite confident that it will work from our model simulations, to gradually scale up the deployment, test it at small scale, try and understand it, and then scale it up. But basically, it's how many megatons of material you put into the stratosphere. So you need to build more aircraft if you want to put more stuff up. But yeah, there's no, I think it would be a bad idea to go from naught to 1 Celsius as fast as possible. You want to do it more gradually.
And thinking about public trust on these kinds of issues, do you think that's one of the biggest, as you said, like when people see this or see you talking about it, or people talking about this issue, they seem to be more willing to take climate action. Do you feel that that's one of the biggest, just a lack of trust in our institutions that we're seeing today? Do you think that's one of the biggest oppositions to this particular type of technology? Or
yes, I mean, I think it's certainly going to be an issue. Yeah, I should say that I was just kind of questioning this. There's an idea that this will definitely lead, or some people think this will definitely lead to a delay in emissions cuts. I was just trying to point out that there's mixed evidence on that. Some people seem to think that or some respondents in surveys suggest that they take climate change more seriously after taking this after coming across this. But the real world, it'd be much more political, and how exactly it pans out is much more difficult. Yeah, but I think the political trust in institutions is eroding. The growth of conspiracies. I mean, there's this chemtrail conspiracy out there that we're already doing some kind of horrible thing somewhere with stuff. Basically, contrails are actually something nefarious. That's not the case, but that's a nonsense conspiracy. But that's already out there, and lots of people believe it. So I think, yeah, there's definitely how to communicate around this and how to work on it. It's going to be very challenging. But it's also very challenging for climate change and everything else. So, yeah.
We've just gone over time, but I'd just like to know what your kind of feelings are about where we're going and the speed at which we need to act, and how likely it is that we'll be able to act. And also, do you ever notice yourself seeing blind spots in your own thinking and just thinking, oh my God, I didn't think about that, or I forget about that from time to time, and not accounting for like every single part of the hyper-object of climate and biodiversity loss?
So that was quite a few different pieces there.
How do you feel about it? And do you ever see yourself or other people missing parts of, how to address the climate crisis? Because it's such an expansive issue. There's always
Well, I think everyone comes at it with their own interests and where they think they can make a difference. I think I've been working this idea. I'm interested in it, but of course, I think everyone who works on this issue is clear. This is not a solution or an alternative to climate change. Those of us who think that we should research this, that think this idea should be explored, are all very clear that our primary objective should be to cut emissions as quickly as possible. That we should investigate and develop negative emissions technologies. That adaptation is really critical. But what I can contend is, there will be considerable suffering regardless of what we do with emissions cuts in the future. And it doesn't look good in terms of, it seems to me that we're not going to hit the 1.5 Celsius target, not by a long shot. And so we're going to see considerable suffering. And if we've got a technology that might substantially reduce climate impacts and hence that suffering, we should explore it and understand it. In terms of blind spots, I think I made one of those issues clear, try to make it clear with, when we do these climate simulations, we hold everything fixed and we do a single experiment. We add SAI and assume the whole rest of the world is constant. Now, that's a kind of an inherent blind spot of climate modeling, because you need to isolate one thing at a time. Now, I mentioned the problem that, what if there is a slip in emissions cuts and in ambition there? That might very well happen. How big a slip could it be? How likely it is to happen? I don't know. But it's not something I can very easily represent in my climate models. It's difficult to do that. So there's a blind spot. There's some blind spots in that sense, which is challenging. But yeah, this is an idea that's it's at an early stage of development, and I think something I didn't make fully clear. I think it's a bit like, are dams a bad idea or a good idea? You can't really say in general that dams are bad or good. You need to look at individual specific dams, how they're designed, how they're run, before you can judge whether it's a good idea or not. The same thing is true of stratospheric aerosol injection. It could be done in a very bad way, governed very poorly, and have terrible consequences. Or we could develop and design it in an optimal way, and it could be an integrated part of climate policy, and it might make a big difference. The details really matter, and so how it develops, what the design is, really matters. And I think there's a lot of work to be done sort of fleshing out that imaginary, that design, before we can get to the position of really judging whether it's a good idea or not.
I think that's a good place to end it. Details matter, and yeah, it's complicated. So thanks very much, Peter. It's been really, really interesting. Yeah, thanks for everyone who's been watching. Had some great questions, and yeah, we'll see you next time. We've got Paul Behrens next month. He'll be talking about population and food, amongst other things. So yeah, look out for notifications about that. So thanks very much.
All right, thank you.
Thank you.
There we go. I'll stop now, Peter.